bureaucracy, stress, tension, and confusion are palpable. Academicians are no exception to that, and academic interaction has also been hampered to a great extent due to this situation. But indomitable spirit of human beings, particularly through searching for more knowledge, teaches us how to prevail over any challenge that we encounter. So, as a humble vanguard of that spirit, the Department of Mathematics, Bankura University, in association with Bankura Mathematical Society of Bankura University, has decided to host a 2-day international webinar on algebra analysis and topology to motivate the young and upcoming researchers in the discipline of pure mathematics to continue their quest in spite of all odds. But please allow me to put a rider also. Though we are hosting such program in the digital platform, this could in no way undermine the conventional chalk and board method of teaching, learning, and face-to-face interaction between the speaker and the audience, or be a substitute to that. On behalf of the organizing committee, I, Dr. Pavel Pal, as one of the conveners of this program, welcome all the honorable dignitaries, eminent resource persons, the audience from different part of the world, and my colleagues. I welcome you all. Now I have the privilege to request our Chief Patron, Professor Debnaran Bandyopadhyay, the Honorable Vice Chancellor of our university, to inaugurate our program. Sir, please.
Thank you very much. It is really very good initiative on behalf of the Department of Mathematics, as well as the Mathematical Society, which has been running for quite a few years in our university. I'm glad to know that they are organizing this international webinar for 2 days involving international and very eminent national speakers in this webinar. This actually a very innovative step. And we know that we are largely affected by this kind of unprecedented crisis, which has forced upon us a kind of social distancing. Despite this social distancing, the academicians are very vibrant in their attempt to bridge the gap through such webinars. Department of Mathematics, all the members of the department are quite active in such matters, and they have been able to involve the international speakers like Professor John MEAKIN of University of Nebraska, Professor ABHIJIT DASGUPTA from the University of Detroit. And I can see that there is also another eminent mathematician, Professor ANAND PRAKASH SINGH. I welcome all of them. And I'm quite sure that this seminar on algebra, analysis, and topology will be a great success. As I have heard from the organizers, that it's going to cross the number of participants is going to cross more than 2,000. That's really amazing. And I really feel proud of my university in the sense that all the departments are very much active in organizing such webinars, not just the postgraduate departments of the university, but also the other 24 colleges affiliated to the university are very vibrant, very active. So that's why every day I can see that the colleges are also organizing such webinars. So I really welcome this initiative, and I also encourage the organizers must think about it I also encourage the publication of an e-book, or maybe the idea of launching an e-journal on behalf of the Department of Mathematics on the basis of the papers that they have been able to collect through this webinar. They may think about it. And the university will come forward to help them in whatever manner possible. So thank you very much, the organizers of the department. But I must regret that I'll not be able to sit through the entire webinar. I'll have to leave because at 7:15, I'll have to attend another short meeting, followed by still another at 8. So thank you very much. I wish this webinar a grand success. Thank you once again.
Sir, thanks a lot for your spirited speech. It is really an appropriate prelude for our program. It would not be possible for us to host such a program without your continuous encouragement. Now, may I request our chief guest, Dr. Shubir Kumar Roy, Registrar in Charge of our university, to deliver his speech. Sir, please.
সেটারে মিউট আছে মনে হয়।
Registrar sir, can you hear me?
বেরিয়ে গেছে নাকি?
He's present.
Oh, just a minute. Yeah. So, thank you, Pavel.
Yes.
Okay. Honorable Vice Chancellor, Professor Devnarayan Bandyopadhyay, all my colleagues in the Department of Mathematics, all the eminent resource persons, both in state as well as abroad, and all the participants. My heartfelt thanks to the Mathematics Department for organizing such an international webinar where all the participants, they will get an opportunity to involve in a serious academic discourse, especially in a moment where the pandemic of COVID-19 is posing a greatest challenge to the very survival and existence of the humankind since Second World War. The pandemic with its ugly face is tormenting the daily life pattern of human beings throughout the world, and already it has stormed with social, political, economical and cultural changes. The world is facing the acute human crisis occurring from a virus about which we have a very little bit knowledge, but it's matter of pleasure when we hear that the states, they are involving in development of the vaccine, and already Russia, it has invented that vaccine. The webinar is on the academic discussion that is regarding the matter of the analysis of algebra and the mathematical discourse. I know it very well. But when I got the opportunity to meet with the people belonging from the arena of science, whether it is mathematics or the other branches of science, I believe that the am I audible? Hello?
Yes, you
Am I
are
audible?
Completely,
Yes.
completely.
Okay. So I believe that the people, when they assembled in a place, naturally beside the academic discourse, they will surely make discussion how to get rid over the different problem what we are facing. So I am sure that this academic deliberation will enhance the cognitive faculty. Uh, this pandemic situation provided also an opportunity for all of us, as our Honorable Vice Chancellor has already said, that regularly all our departments, all our colleges, they are involving in the different webinar, where in the virtual platform we are meeting with the academician across the globe, and we are involving in the serious academic discourse. The similar thing is happening in the mathematics department too. So I am sure that it will immensely benefit the people involved with the academic the discourse of mathematics. So with these words, thanks to all of you. Thanks for your patience hearing.
Sir, thank you
Over to
very
Pavel.
much. Sir, thank you very much for your valuable words. Now, I may request Dr. Ajay Mukherjee, head of the Department of Mathematics, Bankura University, to say a few words about our department. Please, Professor Mukherjee.
Thank you very much, Dr. Paul. Very good evening to our honorable ABHIJIT, registrars, eminent speakers, and my dear colleagues and the participants. Very good evening to all. We are combating against a very tough situation due to COVID-19. However, life has own way to move on, and process of gaining knowledge must go on. Accordingly, seeing it is almost impossible to conduct a seminar face-to-face, we choose digital platform to conduct the webinar. In fact, we started to organize such programs in March 2020 in collaboration with Bankura Mathematical Society. But due to sudden outbreak of COVID-19, we forced to discard the activities temporarily. We really now feel good for being able to organize such programs again in association of Bankura Mathematical Society by means of webinar. The Department of Mathematics, Bankura University, are still in infancy stage, but we think that we have to able to keep steps in the society by means of spreading education in the society. Our students are placed in various fields, including in various academic institutes. In this webinar, we get very good response from all over the world. The participants registered in the webinar are more than 2,000. I think these good response are result of our eminent speakers of the webinar. We are indeed very much indebted to them. We expect their blessing in coming days also. I am very much aware that all are eagerly waiting to hear from the speakers rather than to listen my words. So I will take no more time, but going to next part of the webinar. Very good evening to all. Over to Paul.
Thank you, Professor Mukherjee.
Okay.
Now I request again, Professor Mukherjee, please introduce our first speaker, Professor MEAKIN, and then we can start our formal academic session.
Okay. So, thank you again, Dr. Paul. We are now entering the core of the webinar. I am going to invite Dr. John MEAKIN, MILTON MOHR Professor Emeritus, Department of Mathematics, University of Nebraska, Lincoln, to deliver his talk. But before that, I would like to say a few words about him. John MEAKIN is a MILTON MOHR Professor of Mathematics at the University of Nebraska, Lincoln, USA. He served as chair of the Mathematics Department at Nebraska from 2003 to 2011. His research interests are primarily in the algebraic theory of semigroups, its connection to other fields such as geometric group theory, topology, operator algebras. He has published over 75 research papers in major international research journals. His research has been supported by numerous research grants, including around 25 grants from the US National Science Foundation and the US Department of Education. He has held visiting position in several universities and research institutes in Australia, Belgium, China, Italy, India, Spain, and the USA. He has given well over 200 invited talks, lecture series at various universities, international conferences in around 30 different countries around the world. He is a founding member of the editorial board of the International Journal of Algebra and Computation and served as the journal's managing editor since 2019 to 1990 to 2010. He is an elected fellow of the American Mathematical Society. The title of his talk is Inverse Semigroup and Leavitt Path Algebras. I repeat, the title of his talk is Inverse Semigroups and Leavitt Path Algebras. I would like to request Professor MEAKIN to take over from here. Sir, Professor MEAKIN, please, sir.
Thank you very much. And my thanks to Bankura University for organizing this event and for inviting me. It's a real pleasure to be at least virtually back in India, if not physically. Now, there will be about a 1-minute delay while I load my talk, and I should tell everybody that I am a novice at this format, so I apologize in advance for any kind of technical issues that I might inadvertently create. But let me take 1 minute to try to load my talk. Pavel, can you hear me? Is the audio?
Yes,
Yeah. Okay.
Completely.
All right. I will start loading the talk.
Yes.
No, that's not where it is.
Present now. You have to hit present now. It is the lower.
Yes, just a minute. Yes, I hit present now, but that didn't work. Let me just try it again.
Yes.
Present
Your
now.
PDF is open, I think.
PDF is open.
Okay.
No, that's not it. PDF should be open.
Yes. If it is minimized, then maybe there is some problem to recognize it.
Yeah, so what should I do? It's minimized.
Better first click your PDF first now.
Yes.
From the lower panel of your screen, first click on your PDF.
Yes, I did that.
Okay. Then again click the Google Chrome button.
Okay, Google Chrome. Google Chrome button. Okay.
You are seeing us, I think.
I'm seeing you.
Yes.
But I do not see my PDF on the screen. Let me just cancel that and start again. I'll present now again.
Yes.
And then a window.
You have to hit the present now button first. Then you should choose a window.
Yes, I did that.
There you cannot find your presentation.
I do not find the presentation on the window.
If the PDF is open, you are saying
PDF
that is open.
PDF is open. That's strange.
No issue. Try again.
Here we go. Here it is.
Okay.
It's now there.
Not. Yes. Yes.
Okay, let me maximize it.
Yes.
Is it now visible?
Yes, completely. Your deleted graphs, that page is open now.
It is amazing. It is a miracle. So, so perhaps I could begin my talk. Should I begin my talk at this point, or wait a little?
No, sure, completely.
All right. So let me first of all say a word about my co-authors. I have two co-authors. David Milan, who was a former student of mine, and he's actually an expert in operator algebras. He works at the University of Texas at Tyler. And Zhengkan Wang is a semigroup theorist working in Southwest University, China. He visited me maybe 6 months. He visited me for about a year. And we got interested in graph inverse semigroups and wrote a paper about graph inverse semigroups. And then we thought, well, since graph inverse semigroups are very closely related to things called Levitt path algebras, we might investigate what we could do about Levitt path algebras, or if we could add anything to the literature about this subject. So we were interested in the connections between inverse semigroups and Levitt path algebras. And so we obtained a few results in this direction. I don't claim to be an expert in Levitt path algebras, but I know a little bit about them, and I know a fair bit about inverse semigroups, and it seems that one can say something at least about Levitt path algebras using inverse semigroups. So let me first of all show you a photograph of W.G. Levitt. Levitt, as it turns out, was a colleague of mine at Nebraska. He spent his entire academic career at Nebraska. This photograph was taken, he was a generation older than me. This photograph was taken when he was about 90 years old. He was an active mathematician well into his 90s. He published papers in, I think, 8 different decades. So he was a very prominent mathematician. He was a ring theorist, a non-commutative ring theorist. And his interest actually was not in things that are currently called Levitt path algebras, but in what is known as the probably the invariant basis problem for rings. So what do I mean by this? So he was interested in knowing whether if you take a ring R.
Excuse me, Professor MEAKIN. Excuse me, can you hear me?
Yes.
Yes, there is a small problem in YouTube live streaming, not a very big one. Can you? I request you. Can you please stop your turn off your presentation and again present it? That means I want to have you just off for your presentation and then start it again.
Oh, you want me to start again?
Actually, your page is changing, but in YouTube live stream, the page is not changing. That is sometimes this problem happens. You just stop your presentation and again start it.
Stop sharing? You want me to stop sharing?
Yes, for once. Yes.
Okay. I've stopped sharing, but now I have to start again.
Yes, sir. Just in a similar fashion.
Okay, let me, okay. Shall I present again?
Yes, sir. Yes, sir. Just
okay. Let me try again.
Yes.
Share?
Yes.
Does it work?
Yes.
All right.
I'm sorry for interrupting you.
No problem.
Yes.
Now, is it visible?
Is it visible completely?
So I should continue then, right? Or do you want me to start from the very
start from the picture of Professor Levitt?
So So I don't know who heard what I said about Professor Levitt, but he was a colleague of mine at Nebraska. I knew him very, very well. He was a good friend, in fact, but a generation older than me. He spent his entire career at Nebraska. And this is a picture when he was about 90 years old. He was very active well into his 90s and published a lot of papers, but he was a ring theorist. And so his interest was in the invariant basis problem for rings, which is essentially this question. Now, is this visible, Pavel? Is this okay? Pavel? I'm assuming this is okay. So the
Yes,
question is,
it is okay now.
Oh, okay.
Okay.
So if you start with a ring R and look at the left R modules, R to the M and R to the N, and they're the free left R modules, R to the M and R to the N, and they're isomorphic, does this imply that M equals N? Now, I think everybody knows that if R is a field, all we're looking at is a vector space here of dimension M and dimension N, and everybody knows, from every undergraduate knows, that the dimension of a vector space is an invariant. So the answer to this question is yes, if R is a field, and it's also yes, as it turns out, if R is a commutative ring, but it's not true if R is, in general, if R is a non-commutative ring. And this was the topic of Professor Levitt's research in the 1950s and 1960s. So he wrote a very influential paper called The Module Type of a Ring, published by the Transactions of the American Mathematical Society in 1962. And what he did in this paper is he constructed an F algebra. F is a field corresponding to positive integers, M and N, different integers, which does not have the invariant basis property. So in fact, the free left R modules out of the M and out of the N are isomorphic. So in particular, if M is 1, this algebra, L of 1n, is actually a simple algebra, and the free left R modules R and R to the N are isomorphic. So it's this gadget that is the inspiration for the topic of Levitt path algebras. So this algebra was generalized independently by two groups of researchers, as you can see on the slide here. Both papers actually were submitted in about 2004, but due to issues with getting things published, it took a couple of years before they actually hit the print. So these are the two original papers about Levitt path algebras. And so now let me proceed to tell you exactly what a Levitt path algebra is. So first of all, you notice that Levitt path algebras are algebras associated with directed graphs. So I think we all know what a directed graph is, but let me set up some notation for directed graphs. So gamma will be a directed graph. Every graph has vertices and edges. I think all mathematicians agree on that, but that's about where the agreement ends. Because sometimes graphs are directed, sometimes they have multiple edges, sometimes they don't, and so on. So the set of vertices of the graph will always be denoted by gamma 0, and the set of edges by gamma 1. So every edge E of a graph is directed from some initial vertex, or the source vertex, which I'll denote by S of E, to a terminal vertex, which I'll denote by R of E. Right? So everybody has a picture of a directed edge starting at S of E and ending at R of E. And it's possible that S of E and R of E are equal to each other, in which case the edge is a loop at S of E. Right? So regard these S and the R as functions from the edges to the vertices. So from that point of view, S inverse of a vertex, that's the set of edges that start at the vertex V. And the number of such edges is the out degree of the vertex. So I'll use that notation throughout. And another convention is that for each edge E, this is a directed edge, there's a what's called a ghost edge or a fake inverse edge, E star, that starts where E ends and ends where E starts. And I'll denote, and the function that takes E to E star is assumed to be a bijection, and the ghost edges are disjoint from the original edges. I hope everybody understands this notation. And gamma 1 star will be the set of ghost edges. So we're assuming that gamma 1, that edges and ghost edges are disjoint. So a path in the graph is just a sequence of edges, E1, E2 through En, where EI is either an edge or a ghost edge. So the idea of ghost edges is that you can read edges in both directions. And the range or the terminal vertex of EI is the source vertex or the initial vertex of the next edge. So these are a sequence of edges that are hooked together. The inverse path is just the reverse path with ghost edges attached. So a directed path is a path in which all edges are directed. So they're all in the original set of edges of the graph. And you regard a vertex of the graph as an empty path with, so for convenience, with source and range equal to the vertex. So this is the notation that we're going to use for directed graphs. So with this, I can proceed to the definition of Leavitt path algebras. Now, if you haven't seen this before, it takes a little while to absorb it. But so we're always going to assume that gamma is a directed row finite graph. That means that there's only finitely many edges coming out of any given vertex, and that F is a field, right? So gamma is an arbitrary directed row finite graph. It might be infinite, might have infinitely many vertices, but only finitely many edges coming out of any given vertex. And F is an arbitrary field. It could be a finite field, it could be the real or complex numbers, it could be any field. So the Leavitt path algebra, which I'll denote by L sub F of gamma, this is the free associative F algebra generated by the vertices, the edges, and the ghost edges. So these are generators, subject to these relations that you see on the screen here. So you might just draw a little picture in your on a piece of paper as you're trying to look at these things. It says if you take an edge, let's say you take an edge E, then it starts at the source of E. So the source of E times E is a relation equal to E, and E times the range of E is equal to E. So this is the first set of relations, but that works for E either a vertex or an edge or a ghost edge. So in particular, if E is a vertex, what this relation says is that the vertex is an idempotent. V squared equals V for all vertices. So that's one of the relations. And the other relation, when you choose E to be a ghost edge, if you think about it for just a second, it says E star times S of E is the range of E times E star equals E star for all edges. So these two things near the bottom of the slide are consequences of the first axiom. The second axiom says if you take two distinct vertices, they're orthogonal. The product of them is 0. Now, the third axiom says if you take two edges that are not equal, E and F, and you proceed along E in the negative direction, and you follow that by F, even if even if E and F start at the same vertex, if you proceed along E in the negative direction and then follow it by F, you get 0. Okay, that's an important axiom. And axiom 4 says if you this is the case where E equals F. So if you have a directed edge E and you do E star followed by E, that's the range of E. Okay. So you notice that these 4 axioms have got nothing to do with the addition or the scalar multiplication in the algebra. So these are just semigroup axioms, actually. The last axiom really comes from graph C-star algebras. So it says if you sit at a vertex V and you look at all of the edges E coming out of that vertex, and then you add the E stars over all of those edges, notice this is a finite sum, then you get V. These, so this is for all vertices V that actually have edges coming out of them, that are not sinks. So these are known as the Kunz-Krieger relations. Right, so this is what a Levitt path algebra is. And if the field is the complex numbers, these algebras are very closely related to things called Kunz-Krieger graph C-star algebras, which is a very major topic in the study of C-star algebras. So this is what Levitt path algebras are. They're associative algebras, so they're vector spaces over F. They're also rings, and there's an obvious compatibility relation between the multiplication and the rest of the vector space operation. But they satisfy these kinds of axioms, and they're associated with any directed graph. This is a Levitt path algebra. Okay, if there are any questions, perhaps, I don't know if it works for people to interrupt with questions, but save them anyway for later. However, I would like you to sort of absorb this definition as best you can. This is the notion of a Levitt path algebra. Okay, so the basic examples of this brings the subject alive. So if the graph is a rose or a bouquet of n circles, this is a graph that has one vertex and n directed edges. So I don't know if you can see me gesticulating here. I probably should have put a picture. It's got one vertex and it's got n loops attached to this vertex. That's called the rose, R sub n, or the bouquet of n circles for n greater than or equal to 2. Then the Levitt path algebra of that graph is Levitt's original algebra. Okay, this is the algebra that he wrote the paper about. Remember, that does not have the invariant basis property, regarded as a ring. So that's the first example, the first important example. The second example, well, if you just have a rows of one circle, you don't have more than one, you just have one circle, so it's one vertex and one directed edge. Then the Levitt path algebra is the algebra of Laurent polynomials over the field. So it's also the group algebra of the integers over the field. So the elements of this look like polynomials. They're linear combinations of powers of x, but the powers could be positive or negative, finite linear combinations. So they're Laurent polynomials. So that's a little different from the first example. Even though it looks simpler, it's perhaps a little bit more difficult to understand. And the third example, the third natural example, is if you just take an oriented line graph with n vertices. So all you do is you just draw a line and you mark n vertices from the start to the end on this line, and you put a directed edge between consecutive vertices. So it's just no loops, no cycles, nothing. So the Levitt path algebra of that is simply the algebra of n by n matrices over the field. So this is a very classical object that everybody should be comfortable with. N by n matrices over a field form an algebra. So a reference. I will have references at the end of this talk, but one of the this is the key book on Levitt path algebras. It's a book by Abrams, Ara, and Silas Molina, and it's published by Springer. And you see the reference there. And I can leave you with references to these things. But this is a book, a readable book about Levitt path algebras. That's by now the standard book in the field. This is a very big field. In fact, it just acquired its own American Mathematical Society subject classification number in the new classification scheme. So there's a lot of work done on Levitt path algebras. But these are the basic examples, and keep these in mind because they're different kinds of examples. So it's a very rich field. All right, so here are some basic isomorphism questions that one would naturally ask if you even think at all about this, at least the first one. The first question is, when are two Levitt path algebras isomorphic? In other words, if I give you two graphs, gamma and delta, under what conditions is the Levitt path algebra of gamma isomorphic to the Levitt path algebra of delta? Now, you might think the answer is if and only if gamma and delta are isomorphic graphs, but that's very far from true. And in fact, we don't know the answer to this question, as far as I'm aware. There is a lot of work done on it. This is one of a series of papers by Abrams, Lully, and Pardo in 2008. They constructed, now I'm not going to go into this paper. I will give a reference to it at the end if you want to look in detail. They constructed various change of graph moves that preserve isomorphism of the Levitt path algebra. And they made a major conjecture about when these two algebras are isomorphic under certain restrictions, when the algebras are what are called purely infinite simple. And this is a K-theoretic conjecture, so it's a sort of a deep conjecture. It's been verified in several cases, but as far as we know, it still isn't true, and it also doesn't cover the general case. So as far as I'm aware, this problem, question one, remains open. And I will say a little bit about this problem in some very special cases during the talk. Now, the second question is, when are two matrix algebras over a Levitt path algebra isomorphic? So here you take K by K matrices whose entries are in a Levitt path algebra. And then you take M by M matrices whose entries are in the same algebra, and you want to know when these two matrix algebras are isomorphic. This has got some surprises in the literature. So I'll just mention one theorem by Abrams, Anand, and Pardo in 22. This is a young subject relatively, so it's a subject that people can get into. So it says that Levitt's original algebra, remember, this is the algebra associated with a bouquet of n circles, is isomorphic to K by K matrices over the same algebra. This is very strange that an algebra could be isomorphic to the algebra of K by K matrices over the algebra. That's true if and only if the greatest common, it's a number theoretic result, if and only if the greatest common divisor of K and n minus 1 is 1. Here, I'm assuming n is greater than 1. And the second part of this result says two matrix algebras over Levitt's original algebra are isomorphic if and only if these two greatest common divisors are the same. So this is some positive direction to answering this question too, but it's by no means a complete answer. All right, so these questions will sort of motivate a little bit of what I've got to say today. So now let me turn now to inverse semigroups, which are the tool that I want to use to study some properties, at least, of Levitt path algebras. Now, perhaps many of you already know what an inverse semigroup is. I'm not sure what the audience is, but let me tell you, give you some very basic information about these gadgets. They're also very well studied. There's a book by Lawson, as you see in the middle of the the slide here that gives that's a standard book about inverse semigroups and connects these gadgets with several other parts of mathematics. And it's published in 1998. So for those who don't know about inverse semigroups or want a good reference, that's a good reference. So what is an inverse semigroup? It's a semigroup. I assume everybody has an associative operation such that every element A in the semigroup has a unique element which we'll denote by A inverse. It's a von Neumann inverse. And the inverse has the property that A equals A inverse A, and A inverse equals A inverse A inverse. And the uniqueness is important. That's the definition. You can see obviously from this definition that A inverse and A inverse A are idempotents. In other words, when you square them, you get the same thing, but they're not necessarily equal. So inverse semigroups have idempotence, and E of S will denote the set of idempotents. Now, the standard example of this is if you take a set, a non-empty set, and you look at the bijections between subsets, and you compose them as partial bijections, it's easy to see that a bijection from one subset to another one has an inverse, which is the obvious inverse going backwards, and this one times this one times this one is the original one. Okay, so this is the canonical example of an inverse semigroup. And so inverse semigroups are actually modeled by partial bijections of a set, or more generally, they model partial symmetry in mathematical objects in much the same way as groups model symmetry. So I will need only two very basic facts about inverse semigroups. And for those who are bored with the rest of the talk, you may try to prove the first fact. It's one of the first things proved in the subject. It's elementary, but it's a little tricky. Idempotents commute. In other words, if you take two idempotents of an inverse semigroup, their product in either order is the same. And that means that the idempotents form a lower semilattice where the meet is the product. So, and in fact, that's conversely, if you have a semigroup in which there exists an inverse, not a unique one, in which idempotents commute, it is in fact an inverse semigroup. So the only other thing that I will need is that this idea of a natural partial order on an inverse semigroup, which is defined in the bottom slide. One element is less than or equal to another if it's equal to an idempotent times the other one. Okay, so in a group, the only idempotent is the identity, so this natural partial order is very uninteresting. It's the identity map. But in an inverse semigroup, it's more interesting. Okay, so that's all I think I need really about inverse semigroups. So graph inverse semigroups. Now you remember I said the first four axioms for a Leavitt path algebra are actually axioms for a semigroup. And that's what's called a graph inverse semigroup. So gamma is a directed graph. I define I of gamma to be the semigroup generated by the vertices, edges, and ghost edges, subject to the same four relations that we use to define Leavitt path algebras. So I won't repeat them, but do notice that this means that every vertex is an idempotent, and this last result tells you that E star times the source is the range is E star equals E star for all E. So this is so if you forget the addition and the scalar multiplication, and you don't have that last Kunz-Krieger relation, what you have is a semigroup. In fact, it's an inverse semigroup. Okay, and so this is the object that Jungpan Wang and I began to study, and there's quite a number of papers about these gadgets. It's interesting. So I just mention a couple of very standard things about graph inverse semigroups. The first is that every non-zero element can be uniquely expressed in a canonical form, P Q star. So P means go along this directed path P, Q star means come back in the opposite direction. And P and Q, in order for that to be non-zero, P and Q have to end at the same vertex. So that means R of P equals R of Q. So visualize yourself two directed paths wandering along, maybe very randomly in the graph, and then ending at the same vertex. And then you traverse the path P and you come backwards along the path Q. So every element can be unique, every non-zero element can be uniquely expressed in that form. That's extremely helpful. And when is the product of two such things non-zero? Well, either Q is a prefix of R, or R is a prefix of Q, is the answer. So either Q is, this is the case where R is a prefix of Q, Q is R times some other directed path T. So you go, so to get to Q, you go along R and then you continue a little bit further, right? So, and in that case, it's easy to see what the multiplication looks like. So you do, well, it's written here in this formula, or the dual case. So it's quite easy to understand when the multiplication is non-zero. And it's also quite easy to see that this is in fact an inverse semigroup, and the inverse of PQ star is QP star. So the idempotents are of the form PP star for some possibly empty directed path. So you go up a directed path and then you just come back again. That's an idempotent. In particular, if the path is empty, it says that a vertex is an idempotent. And the natural partial order, RS star is less than or equal to PQ star. Well, it just means that if you look at PQ star and you extend the endpoint by a little bit by T, and R is PT and S is QT for the same T, then that's the definition of the natural partial order in this case. So if you look at that for just a second, you see that the vertices of the graph are the maximal idempotents in the inverse semigroup. So this is, I think, all I'm going to need about the basic ideas of graph inverse semigroups. Now, graph morphisms. A graph morphism is a function that takes vertices to vertices and edges to edges. It's actually two functions, but I'll abuse notation somewhat and use the same symbol, F, and it preserves incidence and orientation, what you would expect. So F of the source of an edge is the source of the image, and F of the range of an edge is the range of an image. And you extend it in the obvious way to F of the inverse edge is the inverse of F of the edge. Now, such a morphism induces maps from for any vertex V tilde in gamma tilde. If you look at all of the edges coming out of V tilde, that maps by the definition somehow into the set of edges coming out of the image, F of V tilde. So we'll denote that map by F sub V tilde. Right, so S inverse of V is all the edges that start with V. The map is called a directed cover if each of these F sub V's is a bijection. So that says if you sit at a vertex and you look at all the edges coming out of that vertex, it maps onto, in a bijective way, all of the edges coming out of the image. And it's called a directed immersion if each of these F sub V's is an injection, not necessarily surjective. So let's forget about the next part. So here is a small result, an easy result about directed immersions into the circle R1, right? So we're just looking at really, really simple case where you're asking what connected graphs immerse into a circle. Well, it's fairly easy to see that such a graph can have at most one sink. That's a vertex that has no edges coming out of it. If it does have a sink, V sub 0, and V is any other vertex, then there's a unique directed path from V to V0. And the graph is in fact a tree, no circuits. And in fact, it's a sink if and only if it admits a directed cover of a line graph. So here's an example. Here, this vertex on the right is a sink, and this graph immerses into a circle. Notice that every vertex here has out degree at most 1, okay, which is, of course, the criterion that you need to get a directed immersion into a circle. So this is a directed cover, actually, of the line graph with 5 vertices, but it's a directed immersion into a circle. And if gamma is not a tree, so remember, gamma is a connected graph that immerses into a circle, then it must have a non-trivial cycle, and any 2 such cycles are essentially the same. They're just cyclic conjugates of each other. And you have a similar kind of result. So let me just show you an example. Here is an example of a directed cover, a finite one. This could be infinite. This could extend infinitely, and lots of trees can come into this circle on the right here. So notice there's a circuit on the right, and everything else in the graph comes into the circle, and everything else looks like a tree, directed tree coming into the circle. And it could come in arbitrary ways, and you can have infinite trees coming into this circle. But directed covers of R1 look like this. So we feel like this is directed immersions into a circle. They are directed covers of a line graph when there's a sink, and these are directed covers of a circle. Okay, so now I need that concept to talk about Levitt path algebras of graphs that immerse into a circle. So we need one more concept, the idea of a zeromorphism and a zero homomorphism. So here S and T are inverse semigroups with 0. So a zero homomorphism is a homomorphism that takes 0 to 0. Okay? It's called zero restricted if, in addition, the inverse image of the 0 of T is exactly the 0 of S. No other element maps to 0. Right? Now it's called so that's the idea of a zero homomorphism and a zero restricted homomorphism, classical sort of thing that everybody's familiar with. A zeromorphism is a slightly different thing. It's a function from between 2 inverse semigroups with 0 that maps the 0 to 0, and it has the homomorphism property if the product ST is non-zero. It just preserves non-zero products. And it's called zero restricted if, in addition, the inverse image of the 0 of T is the 0 of S. Now, zeromorphism is not the same as zero homomorphism. It's very easy to give simple examples of this. I won't labor on the example, but it's clear that a function from S to T is a zero homomorphism if and only if it's a zeromorphism that preserves products that are also equal to 0. Okay, so you can give a simple example, 3-element semilattice mapping onto a 2-element semilattice. The top 2 elements go to the top element of the 2-element semilattice. It's a zeromorphism, but not a zero homomorphism. Okay, so here's the first small result, and this is not very difficult either, but it's interesting because it's something new in the literature. So you start with a graph morphism from gamma tilde to gamma that maps V tilde onto V. And there's an induced function between the graph inverse semigroups. So this function is a homomorphism if and only if it's injective. That's a result by Messian and Mitchell. So this function is not always a homomorphism. The induced function is obvious. It takes P tilde Q tilde star onto the image of P tilde times the image of Q tilde star. This is the morphism. This is the function. It's in general not a homomorphism. It's only a homomorphism if F is injective. However, it's always a zero restricted morphism. okay, between the corresponding graph inverse semigroups that induces zero restricted morphisms between local submonoids. And the interesting thing is that it's a directed immersion if and only if these zeromorphisms, these restricted zeromorphisms, are all in fact one-to-one zero restricted homomorphisms. Okay, so we will perhaps make use of these facts a little bit later. So I think I'm going to skip, well, I'll just mention the examples. If gamma is the circle, then the graph inverse semigroup is the well-known bicyclic monoid, okay? So it's the with a zero adjoined. So it's generated as an inverse semigroup by a set X subject to the relation X inverse X equals 1. Okay, it's also generated as a semigroup by a set X, X and Y subject to a relation YX equals 1. If the gamma is the rows, the bouquet of more than one circle, then the graph inverse semigroup is the polycyclic monoid. Okay, this is a well-known inverse monoid generated as an inverse semigroup by the set X. The relations are X inverse X equals 1 and X inverse Y is 0 if X is not Y. So these are classical examples of inverse semigroups. The polycyclic monoid came up in language theory, actually, as the correct parenthesis language of the syntactic monoid of the correct parenthesis language. So there's a theorem here that's actually not so easy to prove that gives some information about finite directed covers of a bouquet of circles. It says in that case, every local submonoid contains a submonoid isomorphic to the polycyclic monoid. This is not as easy to prove as it looks, but I'll skip that. So now to the main topic that I want to talk about, which is a new class of inverse semigroups that we, for obvious reasons, refer to as levered inverse semigroups. So in general, the multiplicative subsemigroup of a levered path algebra is not very well understood. It is regular, for known regular, if and only if gamma is an acyclic graph, okay? So it doesn't have any directed circuits. But in general, we don't know very much about the multiplicative subsemigroup of the algebra. What I'm calling the levered inverse semigroup of the graph is the multiplicative subsemigroup of the algebra generated as a semigroup by the vertices, edges, and ghost edges. Now remember, the algebra is generated by these same generators, but as an algebra. So as an algebra, you can not only multiply these things together, you can add them and you can scale them, right? We're not doing that, we're just multiplying them together. So here is a small result. Well, actually, it takes a bit of proof. By the way, these references to 2019, this is where an early version of this paper was published by Chung-Pan Wong and myself, was at least put on the archive. The more current version, the more recent version of this thing has got Milan, David Milan, as a co-author, and it's got more results and sort of deeper connections with the literature. However, you can read about most of these results in that archive article. So the first result here says that it's not obvious just from the definition that this is an inverse semigroup even. But it is fairly easy to see that. And the thing that's less obvious is that it's the inverse semigroup obtained from the graph inverse semigroup. It's a homomorphic image of that by imposing one collection of additional relations. Namely, if you have a vertex S of E about degree 1, so the edge E is the only edge coming out of S of E, then EE star is S of E. Now, if you think about it, this is one of the consequences of the Kunz-Krieger relations, if there's only one edge coming out of S of E. But now this is just a semigroup relation. So we have those 4 relations defining a graph inverse semigroup, plus this additional relation. So this gives you a presentation of the thing as an inverse semigroup. Okay? Now this last result here, I think I'm going to skip. It's for people who know something about tight groupoids of inverse semigroups and the work of Excel and Steinberg algebras, but it's an interesting observation. It says the kernel of this map from the graph inverse semigroup to the Levitt inverse semigroup is a well-known congruence that's really important in the classical literature about Steinberg algebras. So I'll skip that. So let me just give you a couple of easy results. So first of all, I'll remind you what a Brandt semigroup is. You take a non-empty set A and a group G. So the Brandt semigroup, which I'll call B sub A of G, that's the triples AGB, where A and B are in the set A and G is in the group together with 0. And the multiplication, I think probably most people listening to this have seen this. AGB CHD, you just multiply the middle group elements in the group if B equals C, and otherwise the product is 0. So this is what's called a Brandt semigroup. It's an inverse semigroup. So the first result here, or the description, if you like, of connected graphs that immerse into a circle, the description of their Levitt inverse semigroups. Well, if gamma is a tree, remember that happens. That happens if it's an immersion, but not necessarily a cover. Then the Levitt inverse semigroup of gamma is in fact a combinatorial Brandt. So the group is trivial, and the sets A and B are both equal to the number of vertices of the graph. So that's a complete classification of what Levitt inverse semigroups of graphs that are trees look like. If gamma is not a tree, well, it's a very similar kind of result, but the group is the integers, the group of integers. It's a Brandt semigroup whose group is the integers. Okay. Now, from that, you can easily classify or determine the structure of Levitt path algebras of connected graphs that immerse into a circle. So if you take a tree, then the Levitt path algebra of the corresponding graph is just gamma naught by gamma naught matrices over the field. Okay. Just assume gamma is finite, so you don't have to worry about this only finitely many non-zero entries, but it works for infinite gamma as well. So if gamma is a tree, the Levitt path algebra is just a matrix semigroup over the field. If gamma is not a tree, the Levitt path algebra is also a matrix semigroup, but it's not over the field, it's over the algebra of Laurent polynomials. So the entries in the matrix algebra are Laurent polynomials. This result, the second result, both of these results are fairly easy to deduce from the previous result, but you can see a different proof of this in a paper by Abrams and co. All right, so now a relatively easy consequence of this, and related to the isomorphism question, if gamma and delta are connected graphs that immerse into a circle, very special class of graphs, and F is a field, then the following are equivalent. The Levitt inverse semigroups of gamma and delta are isomorphic. That's equivalent to the Levitt path algebras are isomorphic, and that's equivalent to gamma and delta have the same number of vertices, and they're either both trees or both have the integers as their fundamental group. Okay. So the fundamental group is this little topological idea that's pretty standard, I think, to anybody with a little basic knowledge of topology. So, so in some sense, this completely tells you when two connected graphs that immerse into a circle have isomorphic Levitt path algebras. It's not a difficult result. But what is a little bit more difficult is that the implication A implies B holds for any graphs, but the converse is false. So if you take any connected graphs, if their Levitt inverse semigroups are isomorphic, then so are their Levitt path algebras. So this gives you some kind of necessary condition for Levitt path algebras to be isomorphic. Now, we gave a proof of this. There's an alternative proof outlined by Excel using his theory of tight representations. And I'll give a reference to Excel's work. It's a very important piece of work. Not this proof, but his general notion of tight representations. But here's a simple example to show that the converse is false. If you look at these two graphs, I'm hoping everybody can see them. Gamma 1 and gamma 2, the only difference is that gamma 2 is missing this loop on the right. Well, the algebras are isomorphic, amazingly. You can read the proof of that. It's not obvious and it's not trivial by a result of Abrams, Lowly, and Pardue in 2008. But the inverse semigroups are not isomorphic, okay? So this isn't, so the theorem is not a necessary and sufficient condition. Now remember, this Levitt inverse semigroup is obtained by taking the four axioms, the first four axioms for a Levitt path algebra, and adding this one other axiom that says if you have a vertex of out degree 1 and you look at the corresponding edge, then EE star is equal to that vertex. So this is what a Levitt inverse semigroup is. Now, here is sort of the meat of the talk. So we'll take it's a little while to absorb this slide. So if you take a directed path, so visualize a path, E1, E2, En, where all the edges are directed, right? It's called a no exit path or an NE path if each vertex, the initial vertex of each edge, has out degree 1. So from the initial vertex of E1, there's only one edge coming out of it, that is E1. From the terminal vertex of E1, there's only one edge coming out of it, that's E2, and so on. From the terminal, yes.
Please excuse me again for interrupting you. There is a similar kind of problem that was happened on the previous time. I am extremely sorry to request you that kindly please do stop your presentation and then again start it. Just
okay, like, I'll stop sharing. I'll stop sharing.
Yes.
Then I'll hope for the best. So I'll escape this.
Yes.
Now let me go back to where do I go? Oh, I have to go to here, and now I have to present now, and I'll do a window again, and we'll hope for the best, and then we'll go to the talk, and we'll share it. And can you see it?
Yes, yes.
Okay, let me maximize it.
Yes, and equivalence on gamma 0, that page is open.
Sorry? It's okay?
Yes, and equivalence relation on gamma 0, that page is open.
Okay. That's where we were.
I'm very sorry.
No problem. I probably did something wrong. But anyway, here we go. Let me start with, so this is a key, Let me see if I can maximize this a little bit. Don't I do Control L or something?
Yes, click on the PDF and type Control L and
click on the PDF and do Control L. There we go. Is that better?
Yes.
Okay. So
Yeah.
hopefully people can see this. So
Yeah.
let me discuss this page. This page is a key idea. So so visualize a directed path P. So it's a sequence of edges E1, E2. Maybe you can see my hands going, right? So so you start somewhere at the start of E1, and then E1 has out degree 1. So the start of E1 has out degree 1. So E1 is the only edge coming out of E1. And the end of E1 has only one edge coming out of it, and that's E2, and so on, right? That's what I mean by a no exit path, NE path. I hope everybody understands that. Now, the final vertex of EN could have all sorts of edges coming out of it, or no edges coming out of it. But the initial vertex of each of these edges has out degree 1. And it's a path, a directed path. So that's the definition of an NE path, no exit path. You also regard an empty path as an NE path. And if you look at it, what it says about an edge is an NE edge if it's the only edge coming out of its start vertex. So that's an NE edge. All right, now I'm going to define an equivalence relation on the vertices of a directed graph. I'm going to define two vertices, V1 and V2, to be equivalent if there are possibly empty NE paths P and Q starting at V1 and V2 and ending at the same place. Okay? So there's NE paths from V1 to the end and from V2 to the end, and they end at the same place. Now, one can prove, not too difficult, that this is an equivalence relation on the set of vertices. And I want to denote the set of equivalence classes by brackets V, and the subgraph induced by these. This is the graph whose vertices are in the equivalence class, but all the edges in the graph are included in the graph. So let me look at an example. Oh, I should say, I'll read all of this and then I'll do an example for you. So hopefully it brings this alive. So each of these graphs, gamma sub V, contains an NE spanning tree. This is a tree inside the graph, I'll call it T sub V. So this is inside this graph gamma sub V, and all the edges of T sub V are NE edges. So it's not only, it's a spanning tree means it hits all the vertices, and it's a tree, subtree of the graph gamma sub V, but it is in fact an NE tree in the sense that all edges are NE edges. So if you take a spanning tree of a graph, you can contract, you can squeeze it to a point. Okay, and so you've got all these spanning trees of these different equivalence classes, and you squeeze them all to points. And you get a new graph, which I'll call the contracted graph, gamma bar, obtained by contracting each NE spanning tree to a point. And there's a natural map from the original graph to the contracted graph. Now, let me just do an example of this. So hopefully it brings it alive a little bit. Here's a couple of examples. Look at the first graph, gamma. Can everybody see? Can you see this graph, Pavel?
I think on that graph pages there is some problem to capture. Otherwise, it is very smooth. So the YouTube, I can see all the Google Meet participants can see those presentations, but YouTube
Okay.
live stream, who are using YouTube live stream, they cannot see this current page. Okay, so two options are there. The same process, you can do it again. They close it and
You want me to do that?
But or and another option is there. I can present your presentation, and you just tell me when to scroll it.
All right. Let's do that.
So, which option will you prefer? The first one or second one?
Yeah, let's do the second option.
Second option.
So
Okay.
if you're able to present
I
this,
think we can see the whole thing. I think we are not having a problem. I don't know.
No, sir. All the Google Meet participants, there is no problem. When
Yes,
this
okay.
page is capturing Google YouTube, there is some problem.
Okay.
Okay.
Because we can see there's no problem for us.
Yes, yeah, I can also see.
Yeah.
So, Professor MEAKIN, can you please you stop sharing? Please stop sharing, and I
you want me
will.
to stop sharing?
Yes, I will start from my computer. Yes. Extremely sorry. I'm extremely sorry. That is some technical issues of Google Meet. I am presenting for you.
Okay. So can everybody see this graph now or still? Pavel, tell me when I should continue talking.
Okay. Can you see my page?
No, I can't see anything. I can see my page.
Okay.
Do you want me to escape from this?
You hit Google Chrome button, then you can.
Yeah. Okay. Google Chrome button. Yes, now I can see you. Well. I can see you off to the side. Are you there?
Yes, sir. I can hear you.
Okay. Well, I would like to go back to that page. I mean, I can't see that page right now.
No. I am on the. Sir, which page do you want that?
I want the page with the two pictures.
Yes.
Okay, you.
Levitt inverse semigroup is previous one. Okay,
You're way after that. Yeah, more.
That one, sir?
No. Keep going. No.
Sorry.
Much further.
Yes. You omitted this one.
This page with the two graphs.
Yes. Sorry. Excellent.
Okay, so now I can discuss this page a little bit, right?
Yes, sir.
So I just want to give an example of this contracting process. So if you look at the graph gamma, let's just focus on the graph gamma. There are red vertices and blue vertices. Yes, is it? Whoop. Okay. So now you notice that the vertex V1, it's gone again. There it is.
Actually, control. If I set that page in full screen, there is some problem. So I think, can you see from this page?
Yes, I can see it.
Okay, sir.
So if I look at this, look at the vertex V1 down the bottom left-hand side of the graph, gamma. There's only one edge coming out of it, right? So this edge is this edge E1 is an NE edge. And V2 has only one edge coming out of it, so it's also an NE edge. Now V3 is not an NE vertex because there are two edges. There's E5 and E, what I call EC1 coming out of it. Yeah. However, notice that from V1 to V3, there is an NE path. Namely, you go E1, E2 to get to V3. And so this says that V1, V2, and V3 are in the same equivalence class. Right? Between any two of these vertices, you can find directed paths starting at each of them and ending at the same place. From V3, it's the trivial path. Okay, everybody see this? So the red component on the left is an equivalence class. And an NE spanning tree of that consists of the edges E1 and E2. Right? Because it's a tree. If you forget the edge EC1, it disappeared again. What happened? No, stay there. Stay there. If you forget the edge EC1, the rest, E1 and E2, forms an NE spanning tree of the red equivalence class. So this process of contracting spanning trees says you just contract both of those edges to a point, those edges vanish, and you get down the bottom of the graph, you see gamma bar, which has a red vertex W1, and the EC1 becomes a loop. That edge remains, but it becomes a loop because the vertices V1, V2, and V3 get identified. So this is what happens when you contract an NE spanning tree. Does everybody see this? You see this? Similarly, on the right, in the blue part, that's an equivalence class. And if you look, you'll see that V4 is, the edge E3 is an NE spanning tree because it's the only, V4 has out degree 1. V5 also has out degree 1. V6 also has out degree 1. And you can get between any two of these vertices by any spanning tree, by any paths from one to the other, from that end in a common place. So the right-hand blue part is also an equivalence class, and you can choose E4 and E3 to be an NE spanning tree. You have some choices here, and if you contract that to a point, the thing I called EC2 becomes a loop, F3. So the result of contracting the top graph by contracting NE spanning trees gives you the very bottom graph, gamma bar. And you can see that if you do delta and you do the contraction, you get, in fact, the same graph. Okay, so hopefully that explanation explains this. Now, Pavel, if you're presenting, can you go back about 2 slides?
Yes.
Back.
Yes. This one.
Okay, this one. So in terms of, go back one more maybe.
Yes.
One more. Yeah. So that was the definition of the equivalence relation and these NE spanning trees and this contracting map. Okay, go forward one graph, one slide. Forward.
Forward. Okay.
Forward, one slide. Okay. This is how you just, in terms of this equivalence relation, you can define the Green's relations on Levitt inverse semigroups. I mean, it's not really worth spending a lot of time on this, but notice that PQ star is D related to XY star if and only if the start vertex of P and the start vertex of X are in the same equivalence class. Okay, so this is very closely related to the Green's relations. And the J relation is a little different. Let me not dwell on this because it's not the main point, but the maximal subgroups of a Levitt inverse semigroup are either trivial or they're isomorphic to the integers. Okay, so one can dwell on this later. Let's go to the next slide. Next slide, Pavel. Okay, here is sort of the main theorem. It's an isomorphism theorem for Levitt inverse semigroups. So first of all, notice that for graph inverse semigroups, there's a result of Messiaen and Mitchell that says, it's a rigidity result. It says, if you take 2 graphs, then the graph inverse semigroups are isomorphic if and only if the graphs are isomorphic. So they don't give you, this inverse semigroup doesn't give you really any information about the Levitt path algebra. It's just, you just refer to the graph. But for Levitt inverse semigroups, you do have a positive result here. If you take 2 graphs, gamma and delta, then the corresponding Levitt inverse semigroups are isomorphic if and only if this happens. First of all, the graphs have to have the same number of vertices. So there's a bijection psi from gamma 0 to delta 0. So that just says the graphs have the same number of vertices, right? And now look at the bottom line of this diagram. It says actually the contracted graphs, gamma bar and gamma delta, have to be isomorphic. There has to be a graph isomorphism between the contract. So you take the original graph gamma and the contracted graph gamma bar, and the original graph delta and the contracted graph delta bar. And remember, you have these contraction maps, chi gamma and chi delta, that do the contraction, that contract the spanning trees. So what this thing says, what this thing says is that gamma, the Levitt inverse semigroups of gamma and delta are isomorphic if and only if there's a bijection between the vertices of the graphs, there's a graph isomorphism between the contracted graphs, and there's choices of any spanning trees for each of the two graphs such that this picture commutes. So for finite graphs, this gives you an algorithm to decide when the Levitt inverse semigroups are isomorphic. You can just check with all the spanning trees, you can check they have the same number of vertices, you can check whether the graphs are isomorphic, and so on. So this is the main theorem, and if I have a little more time, I want to look at some consequences. So can we go to the next slide, Pavel?
Yes, sir.
Well, the next slide is this one. No, stay there. So we already saw that the graph gamma and delta contract to the same graph, gamma bar and delta bar. It's quite easy to see that the conditions of the theorem I just quoted are satisfied. So even though the graphs are definitely not isomorphic, their Levitt inverse semigroups are isomorphic, and therefore their Levitt path algebras are isomorphic. Okay, so these graphs have isomorphic Levitt path algebras. So go to the next slide. I think I'm running out of time. Go to the next slide. Keep going. I think I'll skip that. Next. Here's some, no, forget the proof. Go back. Yeah, yes. Here are a couple of corollaries of the theorem. It says if you take two graphs whose contracted graphs are the bouquet of circles, this is a very special case. That means there's only one equivalence class, okay? Because all the vertices get identified. So if you take two graphs whose contracted graphs are the bouquet of circles, their Levitt inverse semigroups are isomorphic if and only if they have the same number of vertices, okay? Then if you take a finite graph whose contracted graph is a rose, okay, then the Levitt path algebra of gamma. So the first result was about Levitt inverse semigroups. The second result is about Levitt path algebras. The Levitt path algebra of the graph is isomorphic to gamma naught by gamma naught matrices over Levitt's original graph. This is the of Levitt's original algebra. This is the algebra associated with the bouquet of n circles. If n equals 2, the Levitt path algebra of the graph is in fact Levitt's algebra, LF of 1, 2. And if gamma and delta are two graphs which have isomorphic contracted graphs, isomorphic to a bouquet of n circles, a rose where n is greater than 2, then the algebras are isomorphic. The algebras are isomorphic if and only if these greatest common divisors are the same. Okay, do I have more time, Pavel, to do?
Yes, sir. Yes, sir.
Okay, skip to the next.
5 minutes. There is 5 minutes.
Next slide. Skip it. Next slide. Okay, this will essentially be more or less the last slide. Then there'll be some references. So a concept here. So if you have a function between Levitt path algebras, we call it a zeromorphism. So these are algebras now. This function is called a zeromorphism. First of all, it's a linear transformation. So these are, among other things, vector spaces. So it has to be a linear transformation. And then it has to be a zeromorphism between the Levitt inverse semigroups. Now remember, zeromorphism is sort of like a homomorphism. It just preserves non-zero products. Okay? So that's what I mean by a zeromorphism between the algebras. It's called a zero retraction if the Levitt path algebra of gamma is a subalgebra of the Levitt path algebra of delta, and F is a zeromorphism from this is the usual idea of a retraction, actually, from the Levitt path algebra onto its subalgebra that restricts to the identity. So this is the normal sort of idea of a retraction, but there's this zero issue going on. Okay, so it's the idea of a retract in standard idea in algebra. So a theorem says, if you take a graph with finite equivalence classes, if you remember that equivalence relation, and let n be the maximum number of elements in any equivalence class, then the Levitt path algebra of the graph is isomorphic to some zero retract of a Levitt path algebra isomorphic to n by n matrices of whose entries are in the Levitt path algebra of the contracted graph. So the contracted graph tells you a lot of information about the original algebra. So the algebra of the contracted graph, basically matrix algebras over the algebra of the contracted graph give you a certain amount of information about the original algebra. And now this last result, I think I'm going to skip. For those who know about Morita equivalence, I'll just mention it and I'll give a reference to Morita equivalence. The Levitt inverse semigroup of gamma is strongly Morita equivalent to the Levitt inverse semigroup of its contracted graph. I will refer you to a paper of Steinberg for the actual definitions of these things. And at the algebra level, the Levitt path algebra of a graph is Morita equivalent. It's not isomorphic, but it's Morita equivalent, yeah, to the algebra of the contracted graph. Okay, so if you can go down, there's just 2 pages of references. So yeah, the first one, I'll just say a word about these references. The first reference is where this issue about the isomorphism question is raised and the K-theoretic conjecture that I talked about at the beginning. The second reference is the standard book on Levitt path algebras. The third reference is the original paper by Abrams and Aranda Pinto on Levitt path algebras. The next paper gives you some information. I've used this in the talk, although I skipped over it, about the relationship between the algebra and the matrix algebra over this algebra. The next reference is the original reference by Ara, Marino, and Pato on where Levitt path algebras were introduced by them. Remember, they were introduced independently. Excel's paper here is where you can read about tight C-star algebras and tight representations of it's a big, beautiful paper by Excel. If you go to the next page, Pavel, one more page of references. The first reference gives you the C-star algebra analog of Levitt path algebras. This actually predated Levitt path algebras. And an interesting thing is that there have been many results proved for Levitt path algebras and C-star algebras that appear to be the same result, but completely different proofs. And so this was very mysterious, and important work of Steinberg on Steinberg algebras and groupoids begins to clarify this connection. Lawson's book is a standard book on inverse semigroups. Levitt's paper is the original paper on the subject. I'll skip over Lentz. So the archive paper by Jingpan Wang and myself is where most of these preliminary results are posted. But the actual final version is due to 3 authors, myself and David Mylan and Jingpan, and that's in preprint form at the present time. And if you want to read about Steinberg algebras, about Morita equivalence, Steinberg's paper is the place to go. So one more slide, Pavel. And thank you very much. Okay. Thank you. So I don't know now, maybe you have questions or something, or what happens next?
Sir,
By the way,
Professor Mukherjee, please.
Yeah. Thank you. Thank you. It's really our privilege to hear or learn from you. I once again thank you. Thank you for giving your valuable time. Yeah, in spite of many odds. It is now our time of question and answer sessions. Audience in YouTube and the Google Meet may type your questions here in the chat box, and we will consider your questions here. And these questions and answer session will be moderated by our dear colleagues, Dr. Pavel Pal. Over to Dr. Pal, please.
Yeah, I see on the chat box a couple of questions already, so maybe I should answer those questions, Pavel, should I?
Yes, sir. Yes, sir. First, you.
Okay, so the first one is by Aditya Das.
Yes.
Who asks, what is the difference between zero homomorphism and zeromorphism? All right, so a zero homomorphism is actually just really an ordinary homomorphism that takes 0 to 0. A zeromorphism only preserves positive products. Okay, so if you have, so it takes 0 to 0, but it only preserves non-zero products. So if you have two elements S and T of the semigroup with 0 and their product is equal to 0, it's not necessarily true that the image of ST is also 0. That's the difference between a zeromorphism and a zero homomorphism. And there was an earlier slide, I don't know if we can find it, that gave an example. It's easy. There's a 3-element semilattice and a 2-element semilattice. You can see the top of my fingers in the bottom. Can you see this? That's a 3-element semilattice. That's a 2-element semilattice. If you look at the function that takes the top two idempotence of the 3-element semilattice to the top of the 2-element semilattice and takes 0 to 0, well, you can see that if that's S and that's T, then F of S is the top thing in the 2-element semilattice, and so is F of T. So F of ST, F of S times F of T is the top element of the semilattice, but ST is 0, so F of ST is 0. So this is not a homomorphism, it's a zeromorphism. Okay? Because the product of these two things is 0. So that's the difference. Zeromorphisms only preserve non-zero products. Zero homomorphisms preserve all products. Okay, hopefully that answers that question. Okay, yes, thank you. So the next question looked like it comes from somebody called Pavel Pal. I wonder who that is.
No, actually, it was put by some Sangeeta Bhowmik.
Somebody else.
YouTube chat.
Can this directed cover idea work for circle only or other shapes? Well, certainly we can only prove results like that for bouquets of circles. Okay, or for the original question about what the directed covers of and directed immersions of a circle look like, we can only answer for circles. Even directed covers of a bouquet of more than one circle are extremely complicated graphs. So I do not see any good classification of an understanding of directed covers of larger classes of graphs. We can give information about the structure of finite directed covers of a bouquet of circles. That was in a slide that I glossed over, namely the local submonoids of that must contain a copy of the polycyclic monoid. Okay, so that's some structural information. But that's only when you're doing a finite directed cover of a bouquet of circles. if you do, for more complicated graphs, it's extremely difficult to understand. I mean, I don't anticipate any good, real understanding of what these graphs look like. But it is an interesting question, certainly, to study that and to see if you can understand the relationship between the Levitt path algebras of the graph that immerses into another graph and the Levitt path algebra of the other graph. I don't know the answer to that. A lot of things I don't know here.
Sir, another question from YouTube live. Aurobindo Ghosh asked that what is the main difference between graph inverse semigroup and Levitt inverse semigroup?
Levitt inverse semigroup is a homomorphic image of a graph inverse semigroup. So a graph inverse semigroup has four. Can you go back to the slide near the beginning, Pavel? Near the beginning.
Yes.
Yes. I can't do it. Okay. No. Way back. Okay. Way back. Okay. Back to okay. Here's Levitt. This will do. If you look at that will do. What you go back to where you were.
Levitt
okay.
The definition of Levitt path algebra.
Yeah, that'll do because I can explain it from there.
Okay, sir. Yes.
There. If you look at the first four axioms here, so you take a directed graph gamma, rho finite. You look at the first four axioms, that defines a graph inverse semigroup. Okay, the first four axioms. Now look at the last axiom. This involves an addition, right? So this is not an axiom that you can say if in the language of semigroup theory. You've got to use an algebra, right? You've got to be able to add to even formulate this axiom. However, if you look at that axiom and you see that V is a vertex that has out degree 1, right? If V is a vertex that has out degree 1, that means there's only one edge E coming out of V. So this sum just reduces to V equals EE star in that case, right? If the out degree of V is 1. And that last axiom, V equals EE star, if the source of E is a vertex of out degree 1, that is the additional axiom to get a Levitt inverse semigroup from a graph inverse semigroup. So it becomes a homomorphic image of the graph inverse semigroup, okay? And it looks like a very minor thing to do, but in fact, the structure of a Levitt inverse semigroup, the homomorphic images of graph inverse semigroups, and the relationship between the structures is quite difficult. And the kernel of that homomorphism that goes from a graph inverse semigroup to a Levitt inverse semigroup is related to this classical congruence of lengths that connects you with very deep literature in Steinberg algebras and Excel's work on tight groupoids. So there's a nice connection between these inverse semigroups, but when the semigroups are isomorphic is a completely different question, and what they say about Levitt path algebras is also quite different. Levitt inverse semigroups tell you much more about Levitt path algebras than the graph inverse semigroups.
Yes.
I hope that's answering the question.
Yes, sir. One thing I want to ask that from the definition of what I can feel, I am not very expert of that area. I just little bit. I have just gone through a little bit of that. But that inverse structure is coming naturally, I think. So is it possible, sir, to make any general structure, that means some regular semigroup or some restricted structure like Clifford semigroup? Can we generate like this graph inverse semigroup? Can we generate other kind of?
Yeah, well, I think this is a very good question. In general, it would be nice to have some sort of algebraic structure like a semigroup or something that gives you more information about Levitt path algebras than a graph inverse semigroup or a Levitt inverse semigroup. You get very, very restricted information. For graph inverse semigroups, it gives you sort of no information about the algebra, because two graph inverse semigroups are isomorphic if and only if the graphs are isomorphic. So you get zero information about the algebra. For Levitt inverse semigroups, it enables you to sort of handle these NE paths, basically. So vertices of out degree 1, that's the extent to which it can give you information. Now, for arbitrary graphs, where you would like to associate a semigroup or some kind of a algebraic structure, I mean, you would like a structure that you can understand with the property that two of those, and you can decide when two of these structures are isomorphic. You would like to have such a thing with the property that these two structures are isomorphic if and only if the corresponding Levitt path algebras are isomorphic. Okay, but we don't have any such structure. The last axiom 5 that's on the screen here tells you that a semigroup isn't going to do it. You're going to need some other structure to sort of handle the addition.
Yes.
Okay.
Yes.
And the problem is, as soon as you start imposing such a structure, you're more or less just essentially disguising the axioms for Levitt path algebra. So we do not have such a structure. And that would be a very interesting development if somebody could find something reasonable for which we could get an isomorphism theorem like what we have for Levitt inverse semigroups. Okay.
Okay. Okay. So thank you very much. I just stop this sharing. I think.
All right. So I will exit this. I will exit if I can figure out how to do that. Wait a minute. What do I do? How do I get rid of my? Oh, I go over to here.
Yes.
No. Oh, and then I. What do I do? How do I forget how to exit?
No. You just put the Google Chrome button on the lower panel.
Yeah. Yeah. And then?
Can you see me now? See us?
I can see you, yes, but I want to get rid of the
Yes.
presentation altogether. How do I do that?
Which, sir? Please pardon.
Is this okay? My presentation is not showing anymore, right?
Yes. Not showing anything.
Oh, okay.
Then
Then I will mute myself and mute my video so I can hear somebody else.
Yes, sir. Thank you very much. Thank you very much for your presentation. This is a wonderful presentation, actually. And for the limitation of time, we are ending that session, and we are putting forward our next speaker. And I would like to request one of my colleagues, Dr. Sudeep Samanto, to conduct the next session because we are already 10 minutes late, I think. So please, Dr. Samanto, over to you.
Thank you, Dr. Pal. Good evening, everyone. Please allow us to march forward for the next speech and allow me to introduce the next speaker, Professor ABHIJIT DASGUPTA. Dr. ABHIJIT DASGUPTA is a professor in the Department of Mathematics, University of Detroit, Mercy, USA. After completing BSc and MSc in Mathematics from Jadavpur University, he did MA in Mathematics from University of Rochester, New York. He received his PhD in Mathematics from University of California, Berkeley. Before joining University of Detroit, Mercy, he had earlier taught at the University of Louisville, Kentucky, and Jadavpur University, India. His research interests are topology and analysis by using the tools and techniques from mathematical logic and theory of computation. He has also worked in non-standard analysis and philosophy of algorithmic randomness. Today, the title of his talk is Compactness and Finiteness. Now, I would like to request Professor DASGUPTA to deliver his valuable speech. Sir, please.
Thank you, Professor Shamanto, for introducing me. I want to start by thanking everyone from Bankura University. I corresponded with Professor Pal and Professor Mukherjee, and also want to thank the Vice Chancellor and the Registrar, for their introduction, and for everyone at Bankura University and the Mathematical Society there to host this webinar, and for inviting me. I'm honored to be invited to this. Now, first, before I go further, let me ask, can everyone hear me fine?
Yes, sir. You are absolutely fine. You are completely audible.
Okay, so my voice is clear, right? Good. So now what I'm going to do is, again, bear with me, because I'm going to start the presentation here. And let's see, I will start one and see if that works. If not, I'll try something else. So let's try this one first. Can everyone see the screen?
Yes. We can see.
The whole thing is visible, right?
Yes, sir.
So let's see here. Okay, so let me see here. And so here, this is a talk that is quite similar, in fact, almost identical to a talk I had given a few months ago at Jadavpur University in January, 20th of January, I think. And since then, we have obtained a couple of small results, but otherwise, the main thing is the same. Normally, this time of the year, I would be actually in India, Kolkata, and when I met Pavel in January, I was thinking that this time of the year I'll be there, but then this thing happened, so the virus started, and so we are doing everything virtually now. Okay, so let me get started here. My talk, as you can see, will be compactness and finiteness. And so please go to the next slide. So what is compactness? And I'm going to be assuming that everybody is familiar with the standard open cover definition of compactness. A topological space X is compact if every covering of X by a collection of open sets admits a finite subcollection which also covers X. In short, we say every open cover has a finite subcover, right? So as we know, when we teach classes like this, that it's not a very intuitively motivating definition. And so that's something that we always struggle with, and how to teach this thing. So here is one more definition, just for curiosity. I'm going to talk about one more equivalent definition here, and that is it's not as common, but it's actually exactly equivalent to ordinary definition of compactness in topology. And that is, here you can see the definition for any set E. We use this absolute value type notation for the cardinality. Then X is compact if and only if for every infinite subset of A, for infinite subset A of X, there is a point, P, a kind of a limit point, so that every neighborhood of the point will contain as many members of A as the size of A itself. So these are, in topology called complete accumulation points. I think that's the term in some textbooks, and or complete limit points. So a typical limit point, at least in Hausdorff spaces, would be where every point contains infinitely many points of a set. So but a complete limit point is one where every neighborhood of the point will contain the same number of points of the set as there are points in the set. So that is, the cardinality will match. So that's actually equivalent, but it's not used as often. So here is the connection, between compactness and finiteness that I'm going to talk about a little bit, because it's very well known that compactness is something that shows up almost everywhere in math, topology, analysis, of course, and also in algebra and logic very heavily. And it is kind of something we say that compactness is the deep and subtle connection that exists between the finite and the infinite. Well, that claim is of course vague and difficult because we generally only differentiate the finite and the infinite. We normally don't look for similarities, right? When you say finite and infinite, they're completely opposite of each other. So connection between the two, well, I guess that's what compactness is. So our goal is to kind of clarify how compactness relates to finiteness, and this is a kind of folklore in math for at least 100 years that people have studied this connection. And some familiar facts are, you can find this sort of thing in some textbooks, for example, that in Hausdorff spaces, compact subsets behave like finite sets. So for example, finite subsets are closed and, in a Hausdorff space, right? And so are compact sets. And here a finite or point, singletons can be used. So for example, the definition of a Hausdorff space is any two points can be separated by a pair of disjoint open sets containing them, and that just goes to compact sets, right? Any two disjoint compact sets can be separated in a Hausdorff space by a pair of disjoint open sets. And there are other things like if the space is regular also, then you can take a point and for a finite set and a disjoint closed set, and then you can separate them using open sets. Completely regular, you can even get continuous functions separating a compact set and a closed set. So these are familiar facts, but we are going to focus on an idea that's in an exposition by Terence Tao in the Princeton Companion to Mathematics is where we are going to look at. So the idea here is to look at properties which characterize finite sets. So take any property which characterizes a finite set. I mean, the idea of finite set. In other words, take any definition of finiteness, right? So here is some examples that Tao brings in. So here is number one. All real functions on X are bounded. That's Tao calls a local to global. So if you take a function, a real valued function on a set, it's of course bounded on a single point. It's a single real number. But for a finite set, it's going to be bounded on the whole set. So that's that property number one here is a characterization of finite set. A set X is finite if and only if every real valued function on the set X is bounded. So that's one example of a property that characterizes a finite set. Going back to the next one, and this is also from Tao. All sequences from X have constant subsequences. So that's like an infinite pigeonhole principle, right? Take any sequence of points, infinitely many, countably many, infinitely many sequence of points from the set X, then you have to have that, they cannot be all distinct, or, there has to be a constant subsequence. Again, that is true if and only if X is finite. So what Tao points out is, what happens if we put some additional structure on the set X, like a topology, metric, or group. And he observed that once you, put an additional structure, and you look at the corresponding analogous property topological or metric or group theoretic. And then what happens is, the property kind of behaves in a way that we cannot say finite anymore, because there'll be now infinite sets with structure like topology or metric or group that will satisfy those properties. But we can call them, Tao calls them almost finite, and says that this is where where the connection with compactness is. So some example, the space, the unit interval closed is infinite, but it satisfies the topological analogs of the two properties characterizing finiteness, right? So remember, previously we said every real valued function on X is bounded. The topological analog would be every continuous real function on X is bounded. So that's known as pseudo compactness, but that again is a local to global property, right? The second property, again, the topological version of the first Phrygian hole principle. The original non-topological principle was every sequence from X has a constant subsequence. Now the topological version, you replace constant by convergent. So all sequences from X have convergent subsequences. So we can call that the topological principle. Again, these are directly taken from Tao's exposition. Now, what happens is, as Tao points out, if you take general topological spaces, these topological versions are not exactly equivalent to open cover compactness. That's why we have these names like pseudo-compact spaces, are those spaces where every continuous real function is bounded, and so that's not exactly same as being compact in general topological spaces. Then there we have the second property. Every sequence has a convergent subsequence, which is called sequentially compact spaces. And as we know, that again is not exactly the same as compactness in general topological spaces. There are sequentially compact spaces which are not compact, and then there are compact spaces which are not sequentially compact. So yes, so not exactly the same. However, again, as Tao points out, that if you take metric spaces, each of these conditions is equivalent to open cover compactness. So in metric spaces, pseudo compactness is same as open cover compactness, and sequential compactness is same as open cover compactness. And that's actually fairly non-trivial kind of property here. So if you look at this thing, proving that a topological finiteness property like sequential compactness is equivalent to open cover compactness is it's taught in standard undergraduate or graduate courses in topology, but it requires proof, right? It's not absolutely trivial. So that's Tao's idea that compact is almost finite, and so compactness is the topological analog of finiteness. The question is, how do we make this precise? And so I don't have a clear answer, for that. But here is a program that is there in the background, and the program is the following. We can call it the finite compact analogy program. So pick any property that characterizes finite sets, and I gave two examples, right? The first was that every real valued function on the set is bounded. The second one was every sequence of points from the set has a constant subsequence. And then investigate that if you take the corresponding analogous topological property, does that characterize compactness? Now again, so for those two, things were pretty good. I mean, we got, at least in metric spaces, those properties actually characterized open cover compactness, but unfortunately does not always work. Here is an example. So let's take this example here. This is one definition of finite set, or for property that characterizes finite sets. Here is the property. Every injective function from X to X is surjective. We know that that's precisely the definition. One definition of finite sets called it's originally due to Dedekind, then they can define finite sets like this, or rather infinite sets like the negation of this property, that there exists an injective one-to-one function from x into x which is not onto. So that's infinite, and the opposite, every one-to-one function from x to x is also onto, and that's finite. So, if you think of that property, first, you think, okay, let's see, if I take the corresponding topological or metric property, does it characterize open cover compactness? And the answer is no, it does not. First of all, you have to think, if I kind of spend a couple minutes here, you have to think, and you can interrupt me if you want, by the way. Anyone listening to my, while I'm speaking, if you have any question, please feel free, to write. So you can, let's see here. I went to the chat here. Let's come back. You can go to the chat and put a question there, or let me see. I seem to have lost.
Sir, we will put we have decided that we will put the questions after finishing the talk. Actually,
okay, that's fine. So let me go ahead then. All right. So okay. So let me say this. Coming back to this. A set is finite if every injective, a set X is finite if every injective function from X to X is surjective. What would be the topological version of that? Well, you can try continuous. So let's say, try this. X be a topological space. Every continuous injective function from X to X is surjective. Does that characterize compactness? The answer is no, as you can easily find examples, where non-compact spaces satisfying that property, and compact spaces not satisfying that property, and both, so in no way it characterizes compactness. How about metric? Again, for metric spaces, it's false. You can see that if you take the unit interval, there are continuous functions, continuous one-to-one injective functions from the unit interval into itself, which are not surjective, and so therefore it doesn't work. However, if I change continuous to continuity preserves kind of topological stuff, right? Topology of the thing, in a way. If I change that continuous to metric, then it actually works. So here is what works to some extent, at least. So if you take a compact metric space, then it is in fact true that every isometric function from X into X is actually surjective. So in a compact metric space, so every isometric one-to-one function would be actually surjective. It's not true for non-compact spaces. For example, if you take the interval half open interval, 0 to infinity. So let me write that. So here, 0 infinity. Can people see my writing here?
Yes, sir. Yes, sir.
Hello.
Yes, sir.
Yeah, you can see the right. So that's the interval I'm talking about, 0 through infinity. You can shift right by 1, let's say, and then you have a mapping. Let's say x going to x plus 1. That's an isometric mapping from that interval into itself, which is not surjective. It's injective but not surjective. So clearly, so for non-compact spaces that doesn't work, but it is true that if I impose the restriction compact, in a compact metric space, an isometric map will actually be surjective. It's not very difficult to prove. So let me go over to the next thing, which actually brings me to the main topic of this thing. So here is a property that we are going to consider due to Steckel, which is a definition of finite sets, a characterization of finite sets. And Steckel's definition is that a set X, X is finite if and only if there is an ordering on X which is a symmetric well order. Now, what is a symmetric well order? It means both the ordering and its reverse are well orders. Another way to put it is this following: that an ordering on X is a symmetric well order means that every non-empty subset contains both a least element and a greatest element. Okay, so if you take a finite set, any ordering will work. Obviously, any non-empty subset will have a smallest element and a greatest element. But what is slightly more interesting is that the converse is also true. That it's not difficult to prove at all. You can try it yourself. You should be, you're able to see it quite easily, and it doesn't even require axiom of choice. That the converse is also true. That if X can be ordered in such a way, if there is an ordering on X, where every non-empty subset has both a least element and a greatest element, then X must be finite. So that's the property that we are going to focus on, and our goal is to investigate the topological version of this property and see if that characterizes compactness. So I first have to then tell you what is the topological version of this property. That is, what is the topological version of well ordering, and then what is the topological version of symmetric well ordering. And if topological symmetric well orderings exist on a topological space X, then does that mean that X has to be compact? And is that a necessary and sufficient condition? So that's what we are going to ask now. All right, so what is the topological analog of well order? And there are various possibilities, and let's look at this, and this is what we're going to do. So, finite sets are obviously well ordered trivially and symmetrically well ordered. Now, something which is not a symmetric well order, and the simplest example is the set of natural numbers, n. So this is the simplest infinite well order. It's not a symmetric well order, and its continuous analog can be thought of the interval from 0 through infinity, the half-open interval. So, and if you notice, look at this closed 0 through infinity half-open interval. It has this property that every non-empty closed subset has a least element. So that's how we define a topological well order, and that is right here. Topological well order, a linear order on a topological space will be called a topological well order if every non-empty closed subset. So here the idea is that you have a closed subset of X has a least element. So closed interval from 0 through infinity, obviously it's not a well order, but every non-empty closed subset has a least element. So that's topological well order that we are going to use the definition. So here is then our main question, that given that finiteness of sets is characterized by the existence of symmetric well order, like that's Stekel's result, right? A set is finite if and only if there is a symmetric well order on it. Can we characterize compactness of topological spaces by the existence of a symmetric topological well order? So, so symmetric topological well order, does that mean the space will be compact? And conversely. So again, what we'll see is the situation is very similar. I mean, exactly similar to Tao's examples of pseudo-compactness and sequential compactness. That is, the result will hold in metric spaces, but not in general topological spaces. But some partial results will hold, and we'll obtain some results here, which actually goes into set theoretic topology, and some of them are independent of the axioms of set theory. So that's where things get a little bit more technical, but I'm going to avoid all that and kind of so we'll be skipping most of the proofs of the results. So yeah, so first we will focus our attention to Hausdorff topological spaces, and only on Hausdorff. And Hausdorff spaces on which symmetric topological spaces, symmetric topological well orders can be defined will be called Stekel compact spaces. We'll give it a name. And so, and proofs of the results, often involve set theoretic technicalities. As I said, sometimes going beyond the axioms of set theory. And some of the ideas will be, club sets, closed unbounded sets, and stationary sets, reflection, the square principle, etc., which are, I'm not going to assume that you are familiar with all that. So I'm going to kind of leave those out and just focus on what results can be obtained. So yeah, so we avoid all set theoretic technicalities, and we'll have to skip most of the proofs therefore. All right, so here's the definition, which is simple enough. So a Hausdorff space X is Stekel compact. There is some ordering on X, which is a symmetric topological order. Equivalently, X is Stekel compact. The topological space X is Stekel compact if you can define an ordering such that every non-empty closed subset of X, so that's the thing here, closed subset of X has both the smallest and the greatest element. So what is a Stekel compact space? A Stekel compact space is a space which can be ordered, at least in one way, where every non-empty closed subset has the smallest and the greatest element. Okay, so smallest and the largest element. So let's see. Here, one of the things to understand is the ordering has nothing to do with the order topology, and the order topology defined by this ordering is not connected with the given topology of X in any way. So the ordering is kind of totally independent of the topology of X. It can be connected, like in my the examples I'm going to give now, but overall they're independent. So okay, so the unit interval with the usual topology is obviously Stekel compact. Every non-empty closed subset has both the smallest and the greatest element. The unit square also works. Okay, the lexicographic ordering works. And in fact, let me move on here. Some properties of Stekel compact spaces. So again, the question is, in Hausdorff spaces, is Stekel compactness equivalent to compactness? And so we want to study Stekel compactness, and we see immediately that certain properties obviously hold. If a space is Stekel compact under a topology, then it's also Stekel compact under any weaker topology. Every closed subspace of a Stekel compact space is Stekel compact, and so those two are, those two properties are shared with compactness, general compactness, and open cover compactness. And here is another. We don't know if the product of two Stekel compact spaces is Stekel compact. I don't know the answer, but we know that if you take X and Y, two spaces, and X is Stekel compact and Y is compact, then X cross Y, the product with the product topology, is actually Stekel compact. So that's something we know. All right. So here is result. Every compact Hausdorff space is Stekel compact. So not very difficult to prove. It's kind of a generalization of lexicographic ordering result. So and embedding compact spaces into cubes, that is powers of the closed unit intervals. So using that, you can prove that every compact Hausdorff space is Stekel compact. Kind of straightforward. It's also straightforward to prove that every Stekel compact space is countably compact. Both these propositions are so straightforward that you can just do them as exercises. So we have the following result in the Hausdorff spaces. Every compact Hausdorff space is Stekel compact. Implication number one. And then every Stekel compact space is countably compact. Countably compact means every every countable open cover has a finite subcover. There are other equivalent definitions, but that's the definition I'm going to use. In Hausdorff spaces, another equivalent condition for being countably compact is that every infinite subset has a limit point. So, so that's countably compact. So there are two implications. So now, because of the second, because of these two implications, and because in matrix spaces you can actually reverse from every countably compact matrix space is actually compact. So you can go that way. Therefore, in matrix spaces, we have this equivalence, right? Stekel compact if and only if compact. So every matrix space, we see that this property is actually equivalent. All right. Now we want to see if any of the implications can be reversed. So, for example, going back, compact implies stakel compact. Can we reverse that? Stakel compact implies countably compact. Can we reverse that? So those will be our main questions here. So our first result is that stakel compact does not imply compact. In fact, here is an example. You cannot reverse that implication. The space of countable ordinals with order topology, omega 1. Some different notations are used in different books, but the standard set theoretic notation is omega 1, the set of all countable ordinals with order topology. That is a stakel compact space. Requires some proof using ideas of set theory, namely stationary sets. And maybe I'll talk if I have time. Probably not. I'll tell you what a stationary set is. But yeah, so the space of countable ordinals, as is common in topology as a counter example space, it works. It's stakel compact. You can reorder it. Okay, you can reorder it so that every non-empty closed subset will have both a least and a greatest element, but it is not compact. And from that, you can actually derive a corollary that stakel compact spaces may not be normal, which answers a question of Professor TSS R.K. Rao, who asked this question in January when I gave this talk, in Jadavpur University, and he has this question. So that's answered by this result. So the remaining implication is, can that be reversed? So the question is, can we reverse the implication? Stakel compact implies countably compact. So is every So here's the question: is every countably compact Hausdorff space necessarily stakel compact? So this time we don't know the whole answer, but under additional assumptions, and I'll tell you what those are, the answer is yes. So kind of seems like under certain conditions, stakel compactness is close to countable compactness. So to state our main result, I have to give a couple of definitions here. Given a set E, let E prime be the set of all limit points of E. And recall that a set E is called perfect if E prime equals E. So basically, a perfect set is one which contains all its limit points. E prime is a subset of E, but also every point of E is also a limit point of E. So E is a subset of E prime, so they're equal. So those are perfect sets. A space is called scattered if it has no non-empty perfect subset. So, omega 1, the space of countable ordinals, for example, is a scattered space. So the scattered is kind of opposite of perfect, right? Perfect means every point is a limit point, whereas scattered means, well, you might have limit points like omega 1 does, many limit points, uncountably many limit points, but no non-empty perfect subsets. So that's one idea. The second definition is Cantor-Bendixson derivatives or Cantor-Bendixson rank. So what do they mean? If you start with a topological space X, you can take its set of limit points and then kind of inductively go through iterations of the process, right? So for example, we have X0 to be the whole space X, and X1 will be the set of limit points of X, and you can keep going. X2 would be the limit points of the limit points of X, and so on. And at limit ordinals, you take intersections, and you keep going, right? And if you do this to a space like omega 1, you'll see that the space keeps shrinking. So for example, the zeroth derivative of omega 1 is omega 1. The first derivative will be the limit points, the limit ordinals, and the second derivative will be the limit points of the limit points, and so on and on. And you can keep going through the ordinals, and what happens is there will come a point where the process will stabilize. So there will come an ordinal alpha such that X alpha, the alpha derivative, will be equal to the alpha plus first derivative is equal to the alpha derivative. They're the same. And for perfect spaces, that happens right at the beginning, because so the so the CB rank, the Cantor-Bennigsen rank of a perfect space is 0, whereas for other spaces it might happen later. For example, for the space omega 1, the CB rank is omega 1 itself. So it go on uncountably many times before it stabilizes. So it depends on that. So a standard fact is the space X is scattered if and only if the Cantor-Bennigsen rank at that point, the Cantor-Bennigsen derivative becomes empty. So right. All right. So here is now I can state our main result. So this is our main result, and is that if you take a countably compact scattered Hausdorff space X, if its Cantor-Bennigsen rank is less than omega 2. Now omega 2 is the second uncountable cardinal, second uncountable ordinal or cardinal. It's the same thing actually. I mean, let's put it this way: omega 1 is the least uncountable ordinal. Omega 2 is the least ordinal whose cardinality is greater than the cardinality of omega 1. So it has higher cardinality than omega 1, but it's the least such ordinal, and that is much bigger than omega 1, and many uncountably many ordinals come before it. So CB rank less than omega 2 is kind of a large number of steps. So that is our main result, and again, the proof has set theoretic techniques of idea of stationary sets and reflection, so what is the idea of a very rough sketch? Use Cantor-Bennigsen analysis on X and define an order by rearranging the rank points and using reflection via stationary sets. So again, so that's very, the proof is few pages long, and I'm just summarizing it in one sentence, so you can imagine whether that means anything at all. Anyway, so let me just finish quickly by saying what is a stationary set and what is a club set. So a club means closed unbounded. So for example, a subset of omega 1 is a club set if it's a closed unbounded subset of the space of countable ordinals. Here is an analogy with Lebesgue measure on 0, 1. So if you take the set of subsets, measurable subsets, or set of measure 1, set of those are called full measure sets, that forms a filter, and sets in subsets of omega 1 which contain club sets form a similar filter. And stationary is similar to positive outer measure, having positive outer measure. And a result of Luzin and Sierpinski going back more than 100 years is that the unit interval can be partitioned into continuum many pairwise disjoint sets, each having full outer measure. So this is kind of strange, right? So you can split 0, 1 into continuum many disjoint sets, pairwise disjoint sets, each having full outer measure. And that the same thing happens in omega 1. You can partition omega 1 into uncountably many stationary sets. And that's kind of, some of that idea is used to prove our results. So stationary sets are used heavily. Now, beyond that, I skipped the references here. Beyond that, the results were obtained by Joel Hankins and Todd Iceworth, and I want to thank my colleague Yanis Soldatos, who communicated it to them, and they obtained more results. And here are some other results that, if we assume additional hypothesis, going beyond the usual axioms of set theory, which is Gödel's axiom of constructibility, then we can remove this restriction that the CB rank be less than omega 2. So assume V equals L, then every countably compact scattered Hausdorff space is Stekel compact. So now, here are some open questions. Are there countably compact Hausdorff spaces which are not Stekel compact? So open question. Is every separable Stekel compact Hausdorff space compact? We don't know. Is the product of two Stekel compact spaces Stekel compact? So again, these are all open. And I saw in the chat, one of the questions was, is the continuous Hausdorff image of a Stekel compact space is Stekel compact? That's another open question. We don't know. And we investigated that for a while. We still don't have an answer. That's basically where I'm going to end my talk. And thank you very much to everyone for listening. And now time for questions.
Thank you very much, sir. We are very grateful to you for your remarkable speech, and it was so lucid and down to earth that I personally was feeling that it was like a chalkboard teaching. I am observing. I put some questions on the chat box, but before going on to that, I just want to announce two things. First, I want to announce that very well-known and senior professor, Professor Dilip Kumar Ganguly from Department of Pure Mathematics, University of Calcutta, is present here in this Google Meet. Actually, he was present from the first talk, but for some reason we cannot introduce him. Thank you, sir. Thank you, Professor Ganguly, to be here.
Okay, this is a very nice talk. I think Tao, I know Tao. I know Tao because you have Professor ABHIJIT DASGUPTA. You had been in Louisville. So I was in Louisville, but at that time there are a lot of mathematicians, especially in real analysis. They are working over that. And somebody is doing, I know the Miller. I met A. Miller. Have you met A. Miller in Louisville?
No, I don't think he was there when I was there. Although there are
when did you leave Louisville?
I was in Louisville from 1994 to 1995 for a 1 year.
Annie Miller was not there. Annie Miller was not there.
Right.
But one thing is, the answer is question. That symmetric ordering, you have proved that because you know that every OL ordering implies the action of choice. AC. That implies OL ordering implies action of choice. But you have proved the result that about symmetric ordering, but you mentioned that you have not used the action of choice, right? I think. But have you assumed the Martin's action in this case?
No. Let me clarify. Let me clarify and answer your question here. Maybe it was not clear. Here is what when I said it doesn't require axiom of choice. That referred to Stekel's result that a set is finite if and only if an ordering can be defined on the set where every non-empty subset has both a least and a greatest element. This characterization of finite sets does not require axiom of choice. However, all the main result that I that I have obtained, right? And let me see if I can go back to that. So let me see. Somehow my presentation is stuck here. So see if I can go back. Anyway, I'm unable to go back to that slide. But here is the thing that the main result that I obtained, that a countably compact Hausdorff space, a scattered Hausdorff space of CB rank less than omega 2 must be Stekel compact, right? Yeah. That requires axiom of choice, and it does not require Martin's axiom. So it's just pure Zennweller-Frankel set theory with choice. That's where I use that. That's how I prove that. Now, your question is interesting though, because I think the more general result going beyond omega 2, whether they can be proved instead of using V equals L, using Martin's axiom. So that's something that needs to be looked at.
I am Jack Cedar. You know that Jack Cedar. He was when I was in California, in Santa Barbara. Jack Cedar, you know that Jack Cedar is a lot of work done on topology. We use the Martin's axiom to prove on the ordinal space. But because that is why I'm think that you can use also Martin's axiom in the space of ordinality omega 2. Yeah, omega 2.
Right.
Uh,
I,
and other only thing is that
I think there,
what?
Sorry, go ahead. Sorry.
The only thing is this, that only our metric space or everything is both way. But here I have seen that your implication is one way, right? Your implication is one way.
Well, like I said, in metric spaces, it's both ways. So if you take metric space, and a metric space is compact if and only if it is Stekel compact. It's both ways. But in general topological spaces, we have various directions, right?
Thanks.
Thank you very much, sir. Thank you. Before going to some other 2-3 questions, I want to announce one thing. Professor Indranath Sengupta of IIT Gandhinagar is present here, and I am feeling very honored to introduce him. Actually, he is one of our speakers, and tomorrow he will deliver his speech. But now I want to introduce him in this very moment, and from whom I personally learned my basic algebra thing and my love for algebra totally. So, are you there, Professor Sengupta?
Yes, Pavel. Thank you so much. I'm also feeling very happy and very honored to get this invitation and waiting for my talk tomorrow. And it was lovely hearing ABHIJIT talking, of course. It was very nice. So thank you.
Nice hearing your voice, Indro. Nice hearing your voice.
Okay. So maybe I'll just quickly make myself visible also. Okay. So very nice arrangement, and it's so far going on pretty well, and looking forward to tomorrow's my speech. Thank you, and very nice talk again, ABHIJIT. Yeah. And thank you, Pavel.
There are some questions in the chat. Do you want me to quickly go over them? There are some questions in the chat.
I think the question 4 is you have already answered in the open session. You may go through the first 3 questions.
Okay, so let me go through the other questions. Question 4, like Pavel said, by Sadikur Rahman, was something that I already addressed in the talk. That is an open question, a still open question. Question 1 from Sujan Mal is that what is boundedness in topological space? Well, I mean, the concept of boundedness in topological spaces, I don't know how to define it. But what we are talking about, what Tao was talking about in his exposition, is not the boundedness of the space, but boundedness of functions defined on the space. So the idea of that was pseudo-compact spaces, that every real valued function on X is bounded. That function is bounded. So that was I think the idea of connecting boundedness with compactness in topological spaces. So I don't know if that answers the question, but in general, in a general topological space, of course, the concept of boundedness is just simply not there, as far as I know. Question 2 from Chinmay Mishra. Here, let me read the question. The main problem in line is the abstract definition of cover, which themselves are infinite but are representatives of somehow. My question: why is the conversion to topological property so hard? Well, okay, that's a very interesting question. I don't know if I know the answer, and we go ad hoc. So if we have a property of sets and functions where there is no structure yet. So let's say I'm talking about injective functions, bounded functions, etc. Whatever not properties of operations, whatever that may be, sets, functions. Whenever you have additional structure like topology, metric, group, ring, you bring additional structure. I don't think there is a clear answer to the question, what is the corresponding topological version of that property? Or what is the metric analog? Or what is the group theoretic analog? We are always kind of thinking, oh, maybe this is what it is. So if I say that function in topological sense, well, maybe it should be continuous function. Okay, for metric, you have a choice: continuous or preserves metric or uniformly continuous. More options come. Well, you go to algebra, functions, well, morphisms, right, is the obvious analog. Now, there's so many versions of morphisms given your structure. If it's groups, it's simple, but if we have more operations, morphisms become more complex. So this question, conversion to the topological property, is so hard. I take it to mean that how do we figure out the correct topological analog? And I don't know the answer to that. Obviously, that what is the really correct? We just try various things as in mathematics and find out, oh, this must be the real correct version. And in some cases, like metric spaces, there are multiple versions, like continuous, uniformly continuous, isometry, and so on. So I don't know if there is an easy way to, find a topological version of a unstructured set theoretic or function property. Let me go to the last question now. Question 3. Devajyoti Chaudhary asked, what is the necessity of closed set in Stekel compact spaces? Can we have a similar version in open set? Well, again, this relates to actually question 2. So when I define, let's say, topological well order for the space, closed interval from 0 through infinity, half open really, half closed, half open, we can try. Again, the idea is, what is the, obviously that set is not well ordered. We can try to see what is the corresponding topological version of well order would be. And like your question says, what if we try open set? Now we can try, does every open subset of closed interval 0 through infinity have smallest element? It does not, right? And therefore it doesn't seem to work. But for closed set, it works. Every closed subset of the closed interval from 0 to infinity has a, non-empty closed subset has a smallest element. And so therefore we say, okay, closed is the right one. Now, can we do better? In terms of topological concepts, I don't see anything more general that works, So closed seems to be the right one. And obviously there are situations here, and they have been studied, where there are spaces where you might want to ask if we can go to more complicated things, and they can have smallest element, and that's possible. But in this case, I think closed is the simplest that we could get.
Thank you very much, sir. Thank you very much for your wonderful speech. Now we are almost at the end of today's session. Before ending that, I want to hear Professor Hajra, one of our senior colleagues, is present here. He was actually for some technical issues. He was not present at the starting time. So I want to introduce himself to all of our speakers. Professor Hajra, are you there? Professor Hajra, can you hear me?
Yes, I do.
Okay. Actually, I want to introduce you to our speakers. That's why I'm calling you now. So we are at the very end of today's session, and I want to thank you again, Professor MEAKIN and Professor DASGUPTA, for your valuable time and making us mesmerized by your brilliant speech in spite of all odds. And I think, and I would like to announce that tomorrow's session will start again at 7 p.m. And I think so. It is the time to end formally to our today's session. So I want to thank you again, Professor DASGUPTA, Professor MEAKIN, and other dignitaries who are present here, and want to officially close our first day session.
Thank you, Pavel. Thank you, everyone.
Thank you, Pavel. Very nice.
Thank you, sir. Thank you. So we are ending our YouTube live stream. Anyone want to have some chat, you can do it